All right. Thank you for the introductions. By the way, that is Pramod and I am Kranthi. And second last session for the day, so we'll make this very interactive. So at any point, if you have any questions, please feel free to interrupt and ask questions. We're very happy to address then and there. And if something is going in the wrong direction or probably getting extended, we can take some questions offline. All right? So firstly, what is artificial intelligence? How do you see artificial intelligence? This is unusually silent crowd. All right, so yes.
Machine-making decision.
Machine-making decisions. Good. So we have the definition there actually. So this is nothing but developing computer systems to do something which normally require human interventions. Now, over the last few decades, the definition of artificial intelligence kept changing. And one of the earliest instances was back in 1950s when that came up. Any guess what this is?
Server, no.
Computer, close. First computer, close. ENIAC. Anybody watched Imitation Game? It's Turing machine, I would say that's close. This is actually the replica they used for Turing machine in Imitation Game. This is not the actual Turing machine, but a replica of that was used in the movie, but close. So when this was invented, historians later said this is probably AI coming of age. This is like the first step towards something that's going to get really big. But few years later, that happened. What's that historic moment? It's the match between, so this is a match in which Watson defeated Gary Kasparov, that's right. So when this happened, although Kasparov had his own arguments as to why he lost, many people thought that this is the time when AI has finally come of age. Other things that they thought would be possible, they thought these are several decades later they would be possible, but then more recently, this thing happened. It's all written there. This is a game in which Lee Sedol was defeated by AlphaGo. Yeah. So Go is a game which is seen as something that's even more complex than chess. And if any of you play Go, you would understand the complexity involved in this. And the computer had to go through millions of possibilities in order to come up with what's the next best move is going to be. And when the machine defeated Lee with a score of 4-1, everybody was stunned. This is probably a victory for machines. So this is artificial intelligence. Now you might be wondering what this session is about.
So Kranthi covered one part of the name of our topic, demystifying artificial intelligence. So what are we trying to demystify over here, right? So that's the next part. So how many in the audience are people who practice data science, building algorithms day in, day out? I see a lot of hands. How many in the audience are business people who try to solve business problems day in and day out? I see quite a few hands once again. So for both these audiences, the perspective is different, right? For the first set of audience, I'm sure they will be interested in building a self-driven car. For the second set of the audience, I'm sure they'll be interested in how would I predict what is the next product that my customer is going to buy, right? So we have two sets of audience. I have two images over there. What's common? Right, I heard predictions. Any more? Algorithm, bang on. So that's it. I mean, you have business problems, you have artificial intelligence algorithms. Both problems can essentially be solved by the same set of algorithms, and that's what we are trying to convey through this session of ours today. People who practice data science, you can be imaginative enough to solve business problems and just not restrict yourselves to self-driven cars. And people who practice business, they're just algorithms. Things that can solve self-driven cars can also solve your problems, right? Now, having said this, the question that comes into our mind, why now? Artificial intelligence has been here for quite a while. Business problems has been there ever since Industrial Revolution, I guess. So why now?
Technology.
Technology, there's one.
You have more tools.
We have more tools. What else? Lot of data, bang on. Complexity, brilliant. So I think we got the three very important things here. One, big data. So today we are sitting on a huge, we're sitting on data that we couldn't have imagined would exist 10 years ago. And processing power, something that's really important. Earlier, we used to have computers where even if we had to do simple operations, they used to take forever. And now we're building algorithms which crunch millions and millions of data in a matter of seconds. And this is all down to the processing power we have today. And third, algorithms, which for me is probably the most important piece for artificial intelligence. Now, big data is like, if you imagine a human and AI being a human, you can say that big data is more like the backbone. Processing power provides that muscle, and algorithms is like the brain for AI. Now, this is a good analogy. This might have prompted people to ask this question, like, can machines really replace humans in future? Maybe, maybe not. We'll come to that later. But for now, we have a small experiment that would highlight the importance of algorithms and how algorithms built for one purpose can be used in different other situations also.
So demystify. It's difficult to demystify Bangalore traffic and maybe this.
Read through this and keep thoughts to yourself. We'll get back to them.
We have interesting questions following.
Maybe one of you can read.
They're up on the screen. So I'll give you like 5 to 10 seconds. Read through it. Make your own inferences. For the time being, keep it to yourselves. It's supposed to be an abstract poem. I don't understand poems, so. So we'll go for the next poem. Please read through this one also. So I guess most of you have been able to just at least read through it. So by a raise of hands once again, which of the two, so okay, let me put it this way. Who all thought that the first poem was better, or you liked the first poem, or maybe you felt better about the first poem? By a raise of hands. I can see a few hands up. The second poem, I can see a few more hands up.
Looks like some people didn't like either.
Yeah.
We didn't write, so it's okay to like one of them.
We didn't like it either. So now I'm putting it side by side, and I'm going to tell you that one was written by a machine and one was written by an actual human poet, a famous poet. Which one do you think was written by the machine? Which one do you think was written by the left one was done by the machine? How many agree? Left is man. Okay, how many say this is man? I see a lot of hands. How many say this is man? I see, I think an equal number of hands.
It's almost equal.
Yeah.
Some people didn't raise for either.
So the first was written by machine, second was written by man. The point that we want to make is intelligence is something that cannot be really defined, but there are certain benchmarks. And one of the benchmarks was set by Mr. Turing himself, which is we know as the Turing test. And what the Turing test says is that anything that can deceive a human being to be intelligent enough is intelligent. So we just conducted a live experiment of Turing test over here, right? So this one was written by a machine, and a good number of you thought that this was written by a human being, that it has the intelligence of a human being to write poetry, right?
What do you think has actually happened? Like, how did we create this poem? Or rather, how did the machine create this poem?
Yeah, any guesses on what kind of algorithms?
You throw a set of poems to the machine and apply Monte Carlo, probably it would come up with something like.
Yeah, apply algorithms and we can come up with this. That's a good answer. For now, let's forget about different techniques or names of algorithms. Let's just talk simple intuition. How would you train your machine to come up with something like this? Say you have a set of poems written by any poet. Now you want to make your machine sound like that poet. How would you come up with an algorithm? What's the intuition behind this? Placement of words. Yes. Training on data. Yes. So what's basically happening here is, one, the machine should first know language. It should know the grammar. It cannot produce something which says I is sitting somewhere. It cannot say that. I should probably be followed by am. So a noun can be followed by a noun, or it can be followed by proposition, conjunction, or a verb, any of these words. But they come up with some probabilities. In some cases, noun is followed by noun. In some cases, it's followed by other parts of speech. So your algorithm needs to understand the basic grammar, right? In order to build something. And second thing, words need to follow other words. So you know that if your previous word is I, you know that is or is cannot follow I. So it has to be another word. So this is something you can teach the algorithm. So by looking at other poems written by the poet, it can learn the style of the poet. So here this one, the one on the left, we created this using hidden Markov models. So if you, any of you, if you are familiar with hidden Markov models, it basically does two things. So one, it kind of learns parts of speech. Which parts of speech should the next word be, given you have a set of words. And from once you identify the parts of speech, then it identifies the word that should come from that. All right. So you have, say, if xt plus 1 and xt plus 2. So I'm just using some mathematical notation here. So this is the parts of speech. So this is at time t, this is at time t plus 1, this is at time t plus 2. I hope people sitting at the other end also can see that. So this can be a noun, this can be a verb, this can be an adverb, whatever. So at any time you have something like this. What you are getting here depends on what you have before, and probably depends on what you have before that also. And similarly, what you have here depends on what you have before. Now, these we call hidden states. These are hidden. So that's what your algorithm is learning. And what it throws out is a word from this parts of speech that's just identified. So you have yt plus 1, and you have yt plus 2. So the word that comes here, it depends on which parts of speech was selected, and also it depends on what you have before. So this is the basic concept of hidden Markov models, right? So if you actually go through that, you might notice that as a single sentence, the sentences make sense. But if you carefully notice, you might see some disconnect between different lines. And the complexity of these algorithms can be changed in order to make this look more human-like. But this was created using a hidden Markov models, which is looking at the previous 3 states. Now, this is a great example, but business people might be questioning, so what? I mean, we don't need to write poems. Nobody pays us for writing poems, in corporate world. So what is it for us? Let's take an example of, let's look at the retail scenario. Say a person enters a huge supermarket, say something like Macy's or a huge supermarket where you have everything. Now, if you know where the person has been before, and if you can predict where he is going to go next, that's going to add a lot of value, isn't it? So you can plan your structure better. You can know what his needs are. You can give him some real-time recommendations, maybe some real-time offers. You can do all sorts of things. You can manage your sales people better. You can have them at correct places, right? So many advantages with this. And this can be done using hidden Markov models. So the synthetic text generation, that is fancy. That is something we as data scientists would love to do. I mean, to tell someone that I wrote an algorithm which generated this poem for me, isn't it beautiful? It's really cool. But at the same time, at the other end of spectrum, the same algorithm is being used to do something that can really drive business value here. So the point that we are trying to make is, it's the algorithms, the basic intuition behind what's needed, put it in front of a machine and make the machine do it, and that's exactly what we're trying to do here, right?
But Hidden chain also talks about some sequence, right? So you can train it in a sequential order so that it gives a better point.
You mean a simple Markov model? We can do that. We can do that. A simple sequence, you just look at a sequence of words and you can generate from that. So that is a bit...
so sir, how would you define a better point? I mean, it's at the end of the day, it's generated by the machine.
I agree, but maybe in some sequence. I'm not saying
Kranthi.
There are multiple ways we can do this. So you can, instead of going through the hidden states, you're saying that you don't have to really learn the parts of speech. It can directly identify the words and it can throw it like that. So you can try that. So hidden Markov models have proved to be better at synthetic text generation compared to normal Markov models because hidden Markov models provide better grammatical structure to what they generate usually. And we'll come to a few other methods that we could have used here, actually which we used. We'll cover that in later slides. So there's this question that machines, can they really replace humans? Now, let's play a small game. So maybe by end of this game, we'll be able to know whether machines can replace or not. Can you identify the person there?
One answer from here. Sorry, ma'am. Yes?
Steve Jobs. There's Mahatma Gandhi there.
Two Mahatma Gandhi.
Rabindranath Tagore. Can you identify the person there? Albert Einstein. That was very quick.
So this is the first answer.
So the first one was Mahatma Gandhi. So those who have guessed Mahatma Gandhi, you can be proud of yourself because machines will not be replacing you in near future. But others, I cannot say the same thing. Sorry about that. But can you go back to the previous slide? Yeah. So what's really happening? So we saw Einstein there and almost everybody immediately guessed that this is Albert Einstein. I mean, this is not the normal image that we see. Over years, we have seen so many Albert Einstein images and I'm sure this is not one of them. But still you are able to identify. So how does your brain process this? How does it say that this is Einstein?
Based on the patterns?
Based on patterns. What patterns? Hair, face cut. So basically your mind is kind of associating the hairstyle, the face cut, the eyes, probably even the posture also with what you saw in other images. It's linking these features and based on what you saw, the hair might even, I know, don't blame me if I'm deviating too much, but somebody might have said it's Abdul Kalam based on hair. But there are other features which look more like Einstein. And that's probably the reason why you said it's Einstein. So every feature can kind of give you several options, but at the end you're zeroing in on one because that got more weightage compared to the other options you have, right? So now, let's get back to this question. If you have to create an algorithm that can identify, let's say, Gandhi. We, being Indians, let's prefer Gandhi or Einstein. If you have to come up with an algorithm that can identify Gandhi in a set of images, say whether a particular image is Gandhi or not. So how would you come up with an algorithm like that? So you would basically be looking for those features, maybe specs, bald head, the face cut, so nose, lips, some of these features, right? And smile. I don't really remember Gandhi's smile, but my general knowledge is quite poor, so don't mind. Right, yeah, so we look at all these features, individual features. I'll get back.
Yeah, then break it down into a multiple grid, and based on that intensity of the every grid, I can match it up with color.
You're right on point. You're right on point. That's exactly how we can do it. So maybe divide this into blocks and maybe look at those blocks and look for eyes, look for specs, or look for whatever feature we are looking at. Look for multiple features, and by the end, out of the 10 features you look for, if 5 of them say that this is Gandhi, then maybe you can go for Gandhi. That's simple intuition, right? That's how we can look for it. So basically what we are trying to find here is we are trying to have some filters that can look for these individual features. Now there are certain challenges here, because this image is like that, but actual other images that you see in future, they might be quite different, right? So what are those different challenges that you would see when you have to create these filters? So the first one is with the size. So the image can have different size. Pixel size might be different. Or in one, Gandhiji is standing very far, so you just see a smaller version. And in the other image, it's a close-up photo. So you might see slightly enlarged, zoomed version. Or your image can have different levels of illumination. It might be a color image, it can be a grayscale image. So it can vary. And the third one is orientation. It's not just orientation, but also the position of Gandhi in the image. So Gandhi could be in the center of the image, Gandhi could be towards one corner, towards one side, could be anywhere. And you can also have inverted Gandhi. So there are different variations to this. And last but not the least would be surrounding elements. It's not just Gandhiji, there are so many other people. But your algorithm should still be able to say that this is Gandhi's image, right? So these are some challenges that we would see when we create this algorithm. Now, what we'll do is we'll just talk about one algorithm.
So I was going to ask this question as to how would you build an algorithm. Kranthi covered it, and the gentleman over there explained almost this thing, right? We're breaking down the image. So this is a typical flow of any image classification algorithm, right? People who are working on images will very well relate to this. You first get the image, you convert it into a machine readable format, which is like basically numerical vectors. Then you run some filtering algorithms, some post-processing, sharpening, masking, all those different kinds of post-processing to create features which can then feed into our models, which can be as complex as neural networks or maybe something more simpler. But the problem that we are trying to deal over here is a multi-class classification problem, wherein you're trying to identify the type of Gandhi. When he was a young man, after independence, before independence, when he was at old age, that's what we are trying to solve, right? So this would be a typical flow of an algorithm if we are trying to solve this problem. We have post-processing techniques which are not as simple as mean imputation or outlier capping, which involves complex filtering techniques, various convolution methods, concepts from signal processing and all. And then you feed it into some complex classification algorithms. Fine, this is the flow for classification. Just like we had a flow for synthetic text generation. Over there we had how would we solve a retail problem. What problem can be solved over here? Well, we can solve image processing challenges, like for in insurance companies, there is this new buzz about taking photos of destroyed vehicles and then uploading it, and the machine automatically tells you what is the intent of the impact, or the impact of the damage to the vehicle, right? That's a pure image classification application. We had a very interesting application of a similar flow. We borrowed the similar concepts and we happened to apply it in a business scenario. And this was the problem that we were trying to solve. This was for a major oil and gas company in the US. And we had acoustic signals coming from sensors placed on oil pipelines. So just for illustrative purposes, let's say this is the ground level, here is your oil well, and then there are pipelines over here. We have sensors placed over here. It's recording the noise, or not the noise, it's recording the flow of oil within this pipeline. And what the client wanted to understand was that whether we can predict the composition of the oil flowing through the pipeline so that they can know when to pull out oil. Right now what they do is they actually start pumping, they collect some sample, they go to the lab, they test for the composition, then they decide is it mature enough or not, and then they pull out. But over here what we are trying to do is, based on the acoustic signals over here, right, we are trying to predict what is the composition of the oil, whether it's good enough to be pulled out of the oil well or not. This is the challenge. So we know images look like this. How would the data coming from these sensors be like?
Wave.
It's as simple as zzz, right? It's as simple as that. Waves. Waves is the format which our machines will understand, just like the numerical vectors that we had to convert our image into, right? So this data that is coming out of these sensors, we process it into a format that our models understand. We understand the nature of the waves, amplitude, frequency, and all those things. Are there outliers? Do we need to smoothen these outliers? Because this is underground, there will be plenty of noise, right? How do we remove them? And that's where all the concepts of data cleansing of an image signal helps us in also cleaning the audio signals, right? And then once we have a clean acoustic data, we just feed it into one of our classification problems. We had like around, I think 76 different oil types, and around 18 or 20 was good enough for them to pull the oil out. And we built some complex multi-class classification problems. We were able to identify the type of oil flowing in the oil pipelines with very good accuracy. So what do we learn over here? Image classification, people talk about neural nets, deep learning, and everything. It's a big area under research, and it has lots of potential for better learning purposes. They might actually be the true AI in the future. But what we are trying to say is that those concepts are applicable for simple business problems as well, right? So that's what we are trying to, that's the importance of AI algorithms in a business sense. Basically, you can marry the two and you will get solutions for your image classification problems, synthetic text generation problems, and also for your retail problems and problems like this, which pose potentials of billions of dollars, opportunity in terms of billions of dollars. So with that, I'll take a pause. This is about algorithms. Let's take the next step, right? The algorithms, as Kranthi had explained initially, is the brain of our entire system. A user will be a layman, or maybe a person who doesn't understand what's running behind the scenes. So how do we build good interfaces for them, right? So that takes us somewhere to something that we would like to call as intelligent interfaces, right? These are basically interfaces that are able to observe, understand, adopt, learn, and then give responses in a humanly manner. The person does not know, that's the entire essence of the Turing test, right? The person does not really know if he's interacting with a machine or a human being, right? And this is what makes it more personalized. This is what makes it more friendly to your clients, to your users, right? The intelligence is behind the scenes and it has a human mask in front of it, and then your users are interacting with it. That's what we like to call as intelligent interfaces. Multiple algorithms running in tandem behind a nearly human interface providing the perception of intelligence. So for the purpose of this talk, we prepared a small demo. And I'm not sure how many of you attended the session yesterday on the recommender systems. We like recommender systems. So we decided to build a bot. And the bot is what we know to be the closest to human a human mask. Let me call it a human mask, right? So what we're going to take you through is a very quick demo of a movie bot, what we call as a movie bot, whose sole purpose is to recommend you movies. For the time being, we're not taking into any complex business examples. It's just simple movie recommendations. Please. So this is the first use case of the bot. So I'll just repeat the use case. It was of a new user, person interacting with the movie bot for the first time. And I'll just walk you through certain specific points because we want to reconnect with it. More generally, it's just a movie recommendation thing, right? But if you look at the specifics, the way it happened was that I started interacting with the bot. The bot said, hi, hello. And then it asked me, okay, what kind of movies do you want to watch? So it was trying to get information from me. This is something if people familiar with recommendation systems will relate as the cold start problem. It doesn't have data about me. It's trying to build the data about me, right? So now it's asked me, okay, so what movies do you like? I have some suggestions, generic suggestions for you. How would you rate them? And I'll give the bot my feedback that I have watched this, I have watched that, I liked this movie was a masterpiece, movie wasn't like this movie. I give it my feedback. This is basically the bot collecting information about me. And then it makes a first set of suggestions. I say that I have seen some, and so the bot just replaces those movies and gives me new suggestions. That's what happened with the new user use case. And at the end, I was interested about one movie, so I asked the bot, okay, what is this movie about? And the bot tells me, okay, this is what this movie is about. Yes, sir?
One clarification.
Yes.
When somebody has already given his interest,
yes.
then he is loving Godfather.
Yes.
You have a specific type and you can relate it with the other.
Yeah, that's what exactly.
But what happened with the first recommendation? The
What?
first 5 movies.
Yes.
When God has given.
They are basically the global best ones. Yeah, globally the best ones. And so that's the cold start problem, right? What do you predict when the user is new, right? Or you don't have any data about the user. The user didn't log in. He just came to YouTube. What does YouTube recommend you, right? Those things. I'll take it forward. Now, let's assume that it has built history about me. Wait. You need to play back. Yeah, play it from here. This is the last part of the first conversation. So this is the old user. So this was the second use case. The system now has information about me. And when I say that I like the previous movie also, the last recommended movie also, what it tells me that, okay, so it seems like you like movies of this specific actor. I didn't tell it. I didn't realize it probably, I probably myself didn't realize it, that I was liking Al Pacino movies, right? And the system realizes it and it asks me, oh, is it the case?
Why did it pick Al Pacino over Robert De Niro?
I'll have to go back to the movies and check.
No, so the question is how did it pick that
So that's the algorithm that's running in the backend, and I will go to it as to why. It's basically it's trying to you have actors, and maybe there is lots of data that has been built in the backend, and this actor, it seems that there are patterns which show that maybe he likes both the actors, but some numerical value tells the algorithm that this is the movie, which this is the actor that this user prefers over the other. That's the backend algorithm, right?
But does it review all the contents of the movie and like how many stars it got? And
That's how you build a recommender systems, right? So like our friends covered yesterday, that's how you build a recommender system. You have item to item similarity based recommender systems. You have user to user similarity user to user similarity based recommender systems, right? So it depends on the algorithm that's running in the backend. So in this case, our friends had talked about something called as a matrix completion engine towards the end. It's one of the algorithms that's running in the backend over here. It's not the only algorithm. It's multiple algorithms that are working in the backend. Right? You can't stop at one algorithm. Now that actually will bring me to another point. We know that it's pretty obvious that some kind of recommendation engine is running in the backend. Some collaborative filtering, some matrix completion, some algorithm is running in the backend. What do you think are the other algorithms that went into building this bot? And when I say algorithms, it's the concept or the class of algorithm. NLP.
Feature extraction.
I'll write recommendation systems, NLP.
Yeah. Somebody said feature extraction.
Feature extraction. Entity recognition.
What else?
Some of them. Some more?
Sentiment analysis.
Sentiment analysis. Well, I mean, some of them are subclasses of each other. But yeah, these are the classes of algorithms that went behind building this bot, right? But what you saw is a bot which was intelligently and humanly interacting with the user. It was able to give recommendations. It was able to understand probably something that even the user did not realize, like the actor case, right? And it was also able to give more information about some of the movies. Take this to let's say an insurance case, right? An insurance company. I want to buy an insurance policy and I go to their website. Can I not model a similar bot over there? I'm a new user. I don't know about any policies. The bot comes to me and tells me, "Hi Pramod, what do you want?" And then it starts recommending policies, and then it slowly builds my, I look at the various policy options that I have. I finally end up buying one, and then gradually over time, let's say I buy one, then gradually over time the system builds my history. It knows what all claims I have taken, what were the time periods when I have taken I have renewed, did I default any time, and all those things, right? It builds the history of me, right? So it's an intelligent data capture mechanism as well, right? And that's more or less the new user and the old user use cases. We have one more use case. Please play the video.
So this is the case of an odd user. Watch carefully. So the person is actually doing this at a different time. So usually Pramod does it in the evening at around between 4 and 5, but now the time is around 11:30
AM.
So it automatically detected that this is odd time. This is something that's different, not the usual thing. So what is it? What is it doing? Maybe. So,
Kranthi, let the video play.
let
Yeah.
it finish. So here is what has happened. Pramod logged in at a different time, asking for recommendations at an odd time, and it immediately detected that there's something unusual. So it asked, what is it? Is it really you? That kind of question. and Pramod said that he is in a different time zone, so it automatically adjusts its time zone. And now when it comes to recommendations, he's asking for a different genre now. So it immediately said that you usually ask for action movies, but now romantic movies. So maybe new place, new genre, that romantic movies, probably something different. So what is it that's happening here? What did it do initially when he logged in at a different time?
I think we had an answer from the, sorry?
Anomaly detection, that's right. So it detected an anomaly. So we can have some anomaly detections here. And what else? So now that he asked for a different genre, so it started giving options from different genre. And it knows that other users who usually watch that kind of action movies, they kind of watch this kind of romantic movies also. So that's how it's coming up with recommendations. Now let's get back to the insurance example. So suppose somebody met with an accident or something, and the person takes his phone and tries to, so suppose there's an app for the insurance company, and the app is basically acting as his own personal agent. So he tries to enter his claim details. So if there is something unusual about, so something like looking at the person's characteristics, looking at the claim characteristics, the history of claims, if there's something unusual, it can detect an anomaly, it can flag the claim. But at the same time, it cannot say that I won't accept this claim or anything like that. So the flag is, there's a flag, and we can also have some behavioral nudges here, because prevention is better than cure. Rather than taking the claim and then later investigating, probably if you have some behavioral nudges in place, the person can be prompted to be more honest, right? So we can have some behavioral nudges, and at the same time, what the app can also do is, depending on the location or depending on the claim characteristics, it can provide other recommendations, probably as to, not exactly recommendations, but it can help in other ways, as if maybe contact, based on the damage caused, maybe contact a hospital or something, or maybe send somebody for immediate claim processing, depending on the urgency of the claim and things like that. So all these things can be embedded into the chatbot. Yes.
Accident in itself is anomaly. Means I am driving for 20 years and I have committed only one accident. So it is anomaly. So if that happens, then immediately it will flag that, okay, this person is committing a fraud. That is the problem.
Oh, so there's actually a difference between flagging an anomaly and saying that something is fraud. So there's a thin line between them. So saying when something is not fraud, saying that this is fraud has its own repercussions. So a flag will not be generated saying that this is a fraud, but it will only be generated saying that this is an anomaly, something strange, not normal. Maybe the person hasn't made a claim in 20 years and suddenly there's a claim. So maybe he's not driving, maybe his son was driving, who was not even a certified driver, maybe something might have happened. So a flag is natural, but at the same time the nudges are ensuring that the user is being honest in providing the information. So, yes.
And
So for an insurance company, you only reach out to an insurance company when you have an accident. So for them, it is actually not an anomaly, it's a normal behavior.
yeah, so
For an insurance company.
if
The normal is defined by the user data or the company data. So we can discuss.
Yeah. So
you
I
have
just want to point
perfectly-
out one thing. Oh, sorry. I just want to point out one thing. If you notice the bot, it detected that the behavior was unusual, but it ended up recommending romantic movies. So that's the difference between flagging something as a fraud and detecting something as an abnormal or an anomaly. So it's able to do that. It asks questions. Okay, so this is weird. This is weird. It even goes to sarcasm, like new place, new movies, huh? So it does all those things, right? But it doesn't stop there. So
Right. So
this
yeah.
One user history, like each user on their own, but if you make sure it is like say 1 in a million kind of probability, lookalike users.
Right. So it's a problem. It's a modeling problem. When so what you're basically talking about is a modeling problem, looking at other users and accordingly flagging an anomaly. It's not just based on just one user. So this is a modeling problem. So we're only talking at a surface level how the bot does or different capabilities the bot can have. Basically, bringing everything together.
Yeah, so Kranthi, can we write 2 more algorithms over there? I heard anomaly detection and behavioral nudges.
So we got 2 more here.
I just thought the anomaly should have ended by changing my time zone. I said 8 p.m.
Yes. So the
EST.
Yeah.
I said new movies as action. Now
Yeah.
don't start suggesting me a romantic.
no, so the user,
Still at 8 p.m. my local time.
right?
Places could be changed.
And the user asked for romantic movies.
No,
Yeah.
maybe not. You suggested romantic.
No. The
No, so-
user asked for romantic
New
movies.
area, new movies, I said yes.
Yes, and after that he asked, okay, the reason why the bot said new movies is because this person asked, I want romantic movies. We can go back the video.
We can go back. So it was,
Yeah.
Question to that, then does that mean that the bot learns that yes, maybe when this guy goes to a new time zone, he likes a new? Is that then does that
It will be recorded.
considered as a new feature?
It will be recorded. It will be recorded, and over a self-learning process, I mean, this is just one instance that is happening, right? This is one instance. This is the first time it's happening probably. If this has happened in the past, then maybe the bot might not resort to this. If this is, it will identify this person as a frequent flyer or a frequent traveler, then it won't do it. But then if the first time it happens, he flags it. Then for let's say a long time it doesn't happen, then that was a blip in the curve, right? So that's how self-learning happens. You have to, one of the concepts in artificial intelligence is basically reinforcement learning, wherein you don't just look at it in one direction. You at times explore, the concept of explore and exploit. You not only exploit what you know, you also put in some pieces of information in front of the user, like the behavioral nudges and all, to extract certain kind of response from the user to see if what you have learned is correct or not. So that's a concept of artificial intelligence and self-learning loops, right? And
if you are Rajesh Kutrapalli, then you would want to have a companion that you can probably just chat with or interact with. So here is another use case. It's a game that can be played with the bot.
so please play the video. Can you pause when I just raise my thumbs? So let's play the game, right? Let's try to just for entertainment factor. So the game is to guess the name of the movie. Any guesses? Any guesses? Yeah. So that was quick for human beings. It was quick for the bot also. Let's play. Any guesses?
This is the first
Math genius, it says.
Good Will Hunting.
Good Will Hunting, that's right.
Please, please. But the bot says that I don't know the movie. You keep playing. You don't end there. No, please.
Yeah.
Let it complete the.
Serial killer, yes. Stop.
Any guesses? Usual suspects.
No?
7.
7, that's 2 policemen.
We have 3 policemen.
We have
Usual
3 here.
suspect. It's just 2 policemen sitting and Kevin Spacey talking. Okay, let's see what the bot has to say. So the plot is very vague here.
LA Confidential.
Okay. Now the last one. Now the plot is being given in a different way. So what okay. It's Good Will Hunting. So the last example, we put it over there just to give a glimpse of the learning loops, right? You gave an input that it's goodwill hunting, and then it ran some text algorithms in the backend, and then it realized that this can be matched, Mad Demon, Max, Genius, this, that, right? So that was the idea. Okay. So that was the demo, that was the bot. All that we want to try and say is that the interface was so simple. It was very humanly. You were just chatting like you chat in Gmail or Facebook. But the underlying algorithms and the entire concept of intelligent interfaces and the intelligence behind it can be applied in business use cases. Next slide.
We could have given a demonstration of this, but demonstration would have taken more time. So instead we recorded some of our conversation and we just displayed the conversation. But if you would like to see the demonstrations, we would be happy to show it maybe offline, right? So this is fine. I mean, we have all these capabilities to come up with artificial intelligence algorithms and to do some really cool stuff. But of course, there will be some pitfalls. We need to be careful about certain things. Otherwise, we might be running in loops, or we may not get the results that we are really looking for. And there are several issues like that, several things that data scientists need to keep in mind. And the first one that comes to mind is data accuracy. So we need to be extremely careful about the data that we train our algorithms on. So what happened was, recently, someone came up with an algorithm to post some tweets automatically. So it was looking through all the tweets made by users online on Twitter and trying to learn from it, and tweeting on its own. So after a point of time, it became a racist. It started making tweets that were racist. And what just happened? So during the training process, it was probably learning from tweets that are about racism or probably racist tweets. So it's extremely important to have accurate data, so your algorithms don't give unusual results that you do not really look for. The second one is being imaginative about the algorithms. So Pramod already talked about recommendations. So every time a person is asking for some recommendations, say asking for action movies, and it keeps showing some action movies, and later he comes again, he says, based on what I watched before, show me more recommendations. It keeps showing again action movies. He'll never be able to come out of that. He'll never watch romantic movies, he'll never have a girlfriend, so his life will be screwed. That's over. So the thing is, you do not want to design algorithms that capture users in a bubble. So you have to provide them a route or an escape route to get out of it. So maybe if there are 5 recommendations, have 4 action movies and 1 from a different genre. So if he is interested, then obviously his choices will be different, right? And the last one we can talk about is efficient models. And regarding imaginative algorithms, I promised that I would talk about the poems that we created in the beginning. So those were created using hidden Markov models. And alternatively, we also did recurrent neural networks on this. So we kind of trained our algorithm, our recurrent neural network, on all the poems written by this poet, and we tried to make it learn and then create its own poem. So the training process itself, depending on the number of epochs that we used and all, it was taking about 8 or 9 hours every iteration. And every time we get it, we had to again fine tune it. So we spent a week, we finally got a result which was convincing, which was good, but we still chose to display the hidden Markov model for one simple reason. It took about a week to fine tune the recurrent neural network, and guess how much time it took for us to come up with this using hidden Markov models? 20 minutes. 20 minutes is all it took us to come up with that poem there. So what I'm trying to say is your algorithms, so you need to have, you'll have to do a trade-off between accuracy and the total time it takes. Thank you. So maybe sacrificing a bit of accuracy, you can ensure that you're saving so much time. So maybe your algorithms need not be 100% accurate or 90%, even 85% is fine. So it's basically a trade-off. And the last one is efficient models. So the one that we just covered also falls into this, because neural networks usually take a lot of time to learn because there are so many parameters. And at the same time, it's very important to write algorithms which can be quick. So you do not want to go into loops when you do that, and at the same time you want to write efficient algorithms keeping time constraints in mind. So these are a few pitfalls that people can fall into, and this is something that we need to be cautious about as data scientists when we design algorithm that would do some of this cool stuff.
So just as some parting thoughts, I just want to add one thing to what Kranthi said about imaginative algorithms, and this goes back to a question that I got a couple of minutes back as to this is one incident, so does it learn, right? Now, if it were a human being, how would the human react to it? The human would note it as something unusual, and then the human beings have the imagination to like think of various possible scenarios. This might be a fraud, this might not actually be a fraud, this might be on the borderline of fraud or something like that, right? And that's the capability that we want our algorithms in AI, and it depends on data, the algorithms themselves, and the models.
Last question related to last point. The unusualness. See what happens that there are certain, and the language there are certain paraverbal or non-verbal cues. On the basis of that, we understand that whether it is a fraud or not fraud.
Yes.
So which the computer doesn't have. That is the major.
So we are the algorithms right now, as you said, it's the speech, right? It's the speech. So we can have systems that take the speech. As I said in one of those examples, acoustic signals, image signals. Similarly, we can analyze speech. Hidden Markov models work pretty well with speech signals. And then we can understand the sentiment behind it and all those related matters that a human being can also looks into. Maybe not to the level of the human beings, no. But then it can help the human beings make decisions. Whether this was actually, what does the machine say? Does the machine tag this parameter as high or not? And look at all those things. Right? It's if you think of it more as a decision support system, then that's where you want to be. You don't want them to do the job, maybe. Right? So
algorithms need to be very intelligent, like we just covered. So the strength of the model determines how accurate your algorithms are. So this reminds me of one example. So Berkshire Hathaway's stocks, it was noticed that they were rising whenever Anne Hathaway's movies release. And this is probably because of high frequency trading, where some users use some bots to do some high frequency trading. So when an Anne Hathaway movie releases, it automatically captures sentiment and it realizes that there's something positive about this. And so Berkshire Hathaway's stocks kept rising at some point. So the problem here is that when we design this bot, it has to be intelligent enough to know the difference between Anne Hathaway and Berkshire Hathaway. Right.
So with that, we will conclude our session. Just like we show you abstract poems, this is our creation of an abstract art. We have a brain powered by all the different algorithms noted over there, and we have a human interface. Thank you.
Thoughts?